The uses of the coil. Coils have a wide range of applications in various fields due to their ability to generate magnetic fields, store energy, and filter signals. Here are some common uses of coils. In today's video we will discourse on solenoids. Coil are electromagnetic devices that consist of a coil of wire wound into a helical shape, often with a movable iron core inside the coil. They are widely used in various applications where linear or rotational motion is required. Here are some key points about solenoids. Principle of operation. The principle of operation of a solenoid is based on the interaction between an electrical current passing through a coil and the resulting magnetic field it generates. Here's a breakdown of the principle of operation. Coil and magnetic field. A solenoid consists of a coil of wire wound around a core. When an electric current flows through the coil, it creates a magnetic field around it. The magnetic field lines form a pattern, typically concentrated within and around the coil. Attraction and repulsion. If a movable iron or ferromagnetic core is placed inside the coil, the magnetic field interacts with it. Depending on the polarity of the current and the orientation of the core, the magnetic field can either attract or repel the core. Linear or rotary motion. The interaction between the magnetic field and the core produces a force that causes the core to move. In linear solenoids, the core is typically a plunger or rod that moves linearly in or out of the coil. In rotary solenoids, the core is designed to rotate. Energizing and de-energizing. The motion of the solenoid can be controlled by energizing or de-energizing the coil. When the coil is energized by applying a current, the magnetic field is generated, and the core is attracted or repelled, resulting in motion. When the coil is de-energized by cutting off the current, the magnetic field dissipates, and the core returns to its original position due to external forces like springs or gravity. Control mechanisms. Solenoids can be controlled using various methods. Simple solenoids may operate with a basic on-off switch, where the coil is connected to a power source to activate the motion. More complex solenoid systems can involve feedback sensors, control circuits, and microcontrollers to precisely control the duration and intensity of the current, allowing for fine-tuned motion control. The principle of operation of solenoids relies on the generation of a magnetic field by an electric current passing through a coil, which interacts with a movable core to produce linear or rotary motion. This basic principle is applied in various devices and systems where controlled mechanical motion is required. Linear solenoids. Linear solenoids convert electrical energy into linear motion. They typically have a plunger or rod that moves in or out of the coil when the solenoid is energized. Linear solenoids are commonly used in applications such as door locks, solenoid valves, actuators, and automatic door openers. Linear solenoids are electromagnetic devices that convert electrical energy into linear motion. They consist of a coil of wire wound around a cylindrical or rectangular form, with a movable plunger or rod located inside the coil. Here are some key points about linear solenoids. Construction. Linear solenoids typically consist of a cylindrical or rectangular coil made of insulated wire. The coil is wound around a non-magnetic or weakly magnetic form, creating a hollow space inside. The movable plunger or rod, often made of ferromagnetic material, is positioned inside the coil, either partially or completely. Magnetic field and motion. When an electric current flows through the coil, it generates a magnetic field around it. The magnetic field interacts with the ferromagnetic plunger, causing it to move linearly into or out of the coil. The direction of motion depends on the polarity of the current and the design of the solenoid. Force and stroke. The force exerted by a linear solenoid is proportional to the magnetic field strength and the current passing through the coil. The stroke length, which is the distance the plunger can move, is determined by the physical design and limitations of the solenoid. Applications. Linear solenoids find application in a wide range of industries and devices. They are commonly used in various automotive systems such as door locks, trunk latches, fuel injectors, and transmission controls. Linear solenoids are also found in industrial machinery, appliances, medical equipment, and automation systems. Control and activation. Linear solenoids can be controlled by supplying an appropriate electric current to the coil. The solenoid is typically activated by energizing the coil with a specific voltage and current. The duration and intensity of the current can be controlled to achieve precise motion and positioning.
Feedback and control systems. In some applications, linear solenoids are integrated with feedback sensors and control systems to ensure accurate and controlled motion.
This can involve position sensors, limit switches, or feedback loops that provide information about the position of the plunger and enable closed-loop control. Linear solenoids offer a reliable and efficient method of achieving linear motion in various applications. Their ability to convert electrical energy into controlled linear displacement makes them valuable in systems where pushing, pulling, or latching actions are required. Rotary solenoids convert electrical energy into rotational motion. They feature an armature or shaft that rotates when the solenoid is energized. Rotary solenoids are used in applications such as motorized control valves, automotive systems, and indexing mechanisms. Rotary solenoids are electromagnetic devices that convert electrical energy into rotational motion. They are designed to provide precise and controlled rotary movement in various applications.
Here are some key points about rotary solenoids.
Construction. Rotary solenoids typically consist of a coil of wire wound around a cylindrical or disc-shaped form, with a movable armature or shaft located at the center. The armature is made of ferromagnetic material and is free to rotate within the solenoid. Magnetic field and rotation. When an electric current passes through the coil, it generates a magnetic field around it. The magnetic field interacts with the armature, causing it to rotate. The direction and extent of rotation depend on the polarity of the current and the design of the solenoid. Rotary motion control. Rotary solenoids offer precise control over the rotational movement. The rotational angle and speed can be controlled by regulating the current supply to the coil. Advanced rotary solenoids may incorporate position sensors or feedback mechanisms to provide closed-loop control and ensure accurate positioning. Applications. Rotary solenoids find application in various devices and systems. They are used in control valves, locks, latches, indexing mechanisms, switches, and other applications where controlled rotary motion is required. Rotary solenoids are also employed in automotive systems, industrial equipment, robotics, and aerospace applications. Force and torque. The force and torque generated by a rotary solenoid depend on factors such as the magnetic field strength, current flow, and mechanical design. Rotary solenoids can be designed to provide high torque output, allowing them to perform tasks that require substantial rotational force. Activation and control. Rotary solenoids are typically activated by supplying an appropriate current to the coil. The coil is energized to generate the necessary magnetic field for rotation. The duration, intensity, and polarity of the current can be controlled to achieve precise and controlled rotary motion. Rotary solenoids offer a reliable and efficient means of achieving controlled rotational movement in various applications. Their ability to convert electrical energy into precise rotary motion makes them valuable in systems requiring angular positioning, switching, or actuation. Applications. Rotary solenoids find applications in various industries and devices where controlled rotary motion is required. Here are some common applications of rotary solenoids. Control valves. Rotary solenoids are used in control valve systems to regulate the flow of fluids or gases. They provide precise control over the rotational movement of the valve actuator, allowing for accurate adjustment of flow rates or directional control. Locks and latches. Rotary solenoids are utilized in locking systems, such as electric door locks or locking mechanisms in automotive applications. They provide secure locking and unlocking actions by controlling the rotation of the locking mechanism. Indexing mechanisms. Rotary solenoids are employed in indexing or positioning systems where precise angular positioning is required. They can be used in machinery and equipment that need intermittent or incremental rotational movements, such as conveyor systems, sorting devices, or automatic packaging machines. Switching mechanisms. Rotary solenoids can act as switches, toggling between different positions or modes. They find applications in electrical switches, selectors, or relays, where the rotary motion is used to establish or interrupt electrical connections. Robotics and automation. Rotary solenoids are integrated into robotic systems and automation equipment to provide controlled and precise rotational movements. They are used in robotic grippers, pick-and-place mechanisms, and other robotic joints that require rotary actuation. Aerospace and defense. Rotary solenoids are utilized in aerospace and defense applications, such as aircraft actuation systems, missile guidance mechanisms, and aerospace controls. They offer reliable and accurate rotational motion control in critical operations. Medical equipment. Rotary solenoids are found in various medical devices and equipment. They are used in diagnostic instruments, surgical equipment, robotic surgery systems, and medication delivery systems, providing controlled rotational movements for precise positioning and operation. Automotive systems. Rotary solenoids are employed in automotive applications, including throttle control systems, fuel injection systems, transmission controls, and HVAC, heating, ventilation, and air conditioning systems. They provide controlled rotational actuation for improved performance and functionality. These are just a few examples of the wide-ranging applications of rotary solenoids. Their ability to provide precise and controlled rotary motion makes them valuable in numerous industries where accurate positioning, switching, or actuation is required. Advantages. Rotary solenoids offer several advantages that make them suitable for various applications requiring controlled rotary motion. Here are some of the key advantages of rotary solenoids. Precise control. Rotary solenoids provide accurate and precise control over rotary motion. They can be designed to achieve specific angles of rotation and allow for precise positioning, making them ideal for applications that require fine adjustments or precise movements. Compact size. Rotary solenoids are relatively compact in size compared to other types of rotary actuators. Their compact design allows for easy integration into space-constrained systems or devices where size is a critical factor. High torque output. Rotary solenoids can generate high torque output, enabling them to handle applications that require substantial rotational force. This characteristic makes them suitable for tasks that involve opening or closing heavy valves, actuating mechanical linkages, or providing sufficient force for specific operations. Fast response time. Rotary solenoids offer fast response times, allowing for quick actuation and precise control of rotary motion. They can rapidly change between different positions or execute rotational movements with minimal delay, making them suitable for applications that require rapid and precise actuation. Reliability. Rotary solenoids are known for their reliability and durability. They are designed to withstand repeated use and provide consistent performance over an extended period. Properly designed and maintained rotary solenoids can offer long operational lifetimes, reducing the need for frequent replacements or repairs. Ease of integration. Rotary solenoids are typically designed for ease of integration into various systems and devices. They can be easily mounted or attached to existing components, and their electrical control interface simplifies integration into electronic control systems. Energy efficiency. Rotary solenoids can be energy efficient as they only consume power during the actuation process. Once the desired position is reached, they do not require a continuous supply of power to maintain their position, leading to energy savings in applications that involve frequent position changes or holding positions for extended periods. These advantages make rotary solenoids a preferred choice in applications that require precise, controlled, and reliable rotary motion. They are widely used in industries such as automation, automotive, aerospace, medical, and more. Control methods. Rotary solenoids can be controlled using various methods to achieve the desired rotary motion. The control methods can vary depending on the specific application and system requirements. Here are some common control methods used with rotary solenoids. Direct current (DC) control. One of the simplest control methods for rotary solenoids is to directly apply a DC voltage to the solenoid coil. By energizing the coil with a specific voltage and current, the solenoid generates a magnetic field that causes the desired rotation. The rotation can be stopped by de-energizing the coil.
Pulse width modulation, PWM control involves modulating the duty cycle of a square wave signal applied to the solenoid coil. By adjusting the width, on time, of the pulses within a fixed period, the average current flowing through the coil can be controlled, allowing for precise control of the rotary motion. Varying the duty cycle can change the speed or position of the solenoid's rotation. Current control, controlling the current flowing through the solenoid coil can directly affect the torque and speed of the rotary motion. By regulating the current using techniques such as current sensing and feedback control, the rotation can be precisely adjusted to meet the desired specifications. Position feedback control, rotary solenoids can be integrated with position sensors or encoders to provide feedback on the actual position of the solenoid's rotation. This feedback information can be used in closed-loop control systems to accurately control and maintain the desired position or to implement position control algorithms for precise positioning. Microcontroller or PLC control. For more advanced applications, rotary solenoids can be controlled using microcontrollers or programmable logic controllers, PLCs. These control systems provide flexibility in programming and allow for complex control algorithms, motion profiles, and integration with other system components. External control signals. Rotary solenoids can be controlled by external control signals from other devices or systems. For example, a rotary solenoid can be actuated based on input signals from sensors, switches, or other control devices in the overall system. The specific control method chosen for a rotary solenoid will depend on factors such as the application requirements, the precision needed, system complexity, and available control resources. By selecting the appropriate control method, the rotary solenoid can be effectively integrated into the overall system and provide the desired controlled rotary motion.